Well, thank you very much for inviting me. I hope you can see this. I had it originally on PowerPoint, and I didn't expect to be using this. Can you see this okay? The gentleman at the back, can you see? Oh, can you see it? Very good. So, the aim is to first give a very quick introduction, and then a very first look at the forces between elementary particles, and then a second look in more detail, introducing the standard model of elementary particles. And actually, this is a very good story from the nuclear force to QCD, so I'll take that on its own, because it's really like an adventure. For the weak force, it's more difficult, because the weak force breaks the symmetry, and first we have to introduce Lagrangians and local gauge theory and spontaneous symmetry breaking. So I'll do the weak force next. And having done that, if I have a fourth lecture in particle physics, I will talk about grand unified theories and beyond the standard model. And all of these view graphs can be found on the web, on that blue address there. So, starting with the overview, particle physics is concerned with the fundamental constituents of matter. To get to the very basic building blocks of matter, that on its own is more like botany, but what is interesting is the interactions between these fundamental states of matter, and that's the exciting thing. So, what are the fundamental constituents of matter? Well, at the moment, we believe them to be two types. We call them matter particles and gauge particles. And the matter particles all have spin 1/2. And they come in 6 flavors of quark, up and down, charm and strange, top and bottom. And these 3 here have charge 2/3, and these 3 have charge -1/3 in units of the proton charge, or minus the electron charge. And then we also have 6 leptons, the electron, the muon, and the tor, and their respective neutrinos. And they've got charge 0, and these have got, I should have got charge -1 here. This is a mistake, so that should be -1. Now, it's a real puzzle why nature would have been just happy with the first 4. And for some reason, nature Xeroxed itself once and Xeroxed itself again. And there's a Nobel Prize for the person that will answer that. Probably 2 Nobel Prizes, because it's been such a long, outstanding problem. Why nature makes a copy of itself and another copy, which is heavier. Besides these 6 quarks and 6 leptons, there are antiparticles of all of these, which are written with a bar on the top. The antiparticle of the electron is the positron. And then we'll see that the quarks come in 3 colors, but that will come later. So that's the particles. Now what about the gauge bosons? Now the gauge bosons are the force carriers between those matter particles. So we can draw this Feynman diagram picture here, in which the gauge boson is transmitting the force between these 2 particles. Now there are 4 forces between the elementary particles. There's gravity, the electromagnetic interaction, the weak nuclear interaction, and the strong nuclear interaction. Now, gravity acts on all massive particles. So if these 2 particles have mass, then they would exchange a graviton, which has spin 2. We haven't seen the graviton yet, so this is a speculation, but it's confidently expected that eventually it will be seen. It's the other forces that we'll be concerned with here, because this one is quite weak. Electromagnetic, you exchange the photon. The weak interactions, you exchange massive weak bosons. These have got mass, so those are going to be carried across here. And they will give us the weak interaction. And then and they act on all quarks and leptons. They act on the flavors, as we will see. For the strong interaction, they act on the colored objects. So they only act on the quarks and the gluons. The gluons themselves carry color. So the strong interactions act on the color. And all of these three sets of gauge bosons have got spin 1. Now, it's been drawn in this way, where the gauge boson is going across, but the gauge boson could equally well be one of the outgoing particles. So, for example, in electron-positron collisions, producing a W plus and a W minus, you could have outgoing gauge bosons, and then we'd have another gauge boson here. Or we could have another Feynman diagram where we've got outgoing gauge bosons, but the particle mediating the interaction is just one of the matter particles. So it's rather, in a way, an arbitrary division to talk about the matter particles on the previous view graph and the gauge bosons on this view graph. So those are the constituents that we believe at the moment. Now let's quickly talk about the units that we use in particle physics. We're dealing with quantum effects, and we're dealing with particles that go with an appreciable fraction of the velocity of light. So it's natural to measure velocities in terms of the velocity of light and to set the units so that this Planck's constant divided by 2 pi is equal to 1. So those are the units that are conventionally used in particle physics. Now, if you set the velocity of light equal to 1, in these new units, this means that the dimensions of length have the same dimensions as time, because that's a velocity. Planck's constant's an angular momentum, a mass times a distance times a velocity. So there's a mass times a distance times a velocity, and that's equal to 1. Now, if L is equal to t, you see from this that mass has the inverse dimensions of length. Now, we know from relativistic mechanics that we have a relationship between the energy of a particle and its momentum and its rest mass in this form. Now, if we're setting c equal to 1, it means the dimensions of energy, rest mass, and momentum have all the same units. And that's the only unit we need, because if we have a mass given in GeV, then we know what the length is and we know what the time is. And it's conventional to talk about GeV because that's about the mass of the proton. The mass of the proton is 0.94 GeV. Now, we're dealing with small numbers or big numbers in particle physics, and so as prefixes to whatever dimensions we are using, we have in going down in orders of 1,000. We go from milli to micro to nano, pico, femto, atto, etc. Just going down every time by 1,000, getting smaller and smaller lengths. This is about the size of a nucleus, so this is also called a Fermi. And going upwards, we have in units of 1,000 the prefix K, M, G, T, P, standing for kilo, mega, giga, tera, and peta. So, if we look at this setting both h and c equal to 1, if we take the product of them, and in our new units it's equal to 1, and we put in the value in MKS units for h bar, here's h in MKS units, joules seconds, divided by the 2 pi, and then multiplied by the velocity of light in MKS units, meters per second, which is 3 times 10 to the 8, you can see the seconds cancel out. And if we convert that joule into electron volts, we divide by 1.6 times 10 to the minus 19, and we multiply all of this together, we get something about 2 times 10 to the minus 7 electron volts meters. Now, if we increase the energy by 9 and decrease the length by 15 orders of magnitude, the change is 6 orders of magnitude, and that essentially gets rid of this, but for a factor of 10. and so it just comes to be about 0.2. In other words, a Fermi is about 5 GeV to the minus 1. Fermi is typical nuclear size, and we're saying this is a typical nuclear energy. So we are noting that we're using Fermis and GeV. So those are the units that are used in particle physics. So what are the masses of these particles in our GeV units? Now the masses, the electron mass, which is about half an MeV, in GeV is very, very small. The muon, which is about about 100 MeV, is 0.106, and the Tor is considerably heavier. The quarks, the two light quarks in the up and down, are just got masses the order of 3 MeV, 6 MeV. This is 130 MeV, 1.3 GeV, 4.2 GeV, and a massive top quark. Nobody understands why the masses are like this. This is a very strange set of masses. The neutrinos, the other particles, in the standard model, they're massless, so they're way down here. Oscillation experiments show that actually they're not massless because we know that they've got a mass difference between different flavors of neutrino. Cosmology limits the sums of the masses of all the neutrinos to less than an electron volt, of the order of an electron volt. So they're way down here, because this is 10 to the 9 electron volts, so they're way down here. Now the gauge bosons, the photon and the gluon, are massless, and as we've said, these other two are very massive. They're the next massive particle to the top quark, 80 GeV and 91 GeV. So those are the masses. Now the quark masses are a bit of a puzzle, because they are given here. They are extremely light, and you will see in the literature other masses that are about 300 MeV. So what is going on? Well, for quarks, it's quite a problem, because we never see a free quark. A quark is confined in a hadron. And if we confine a quark in a proton, which has got the size of a Fermi, we know that it's got an uncertainty in its momentum, which is 1 over delta x, because remember, h bar is 1, which is the order of a Fermi, and we showed a Fermi was 5 GeV to the minus 1, so it's a fifth of a GeV. So if we were able to translate this straight to mass, that would be the order of 200 MeV. But this is a non-perturbative situation, and it's not easy to translate this momentum to a mass. We know it's of the order of 200 GeV. The empirical values from spectroscopy are such that this is the order of 330 for the up and the down, 500 for the strange, and 1,500 for the charm. That's different to the masses I showed on the previous view graph, which were 6, 3, 130, 1,300. See, these are particularly different. Now, this mass, the mass that's used in the Lagrangian, in the theory, comes about because when you look at that quark inside a proton and you hit it very hard, it acts as if it's free, not confined, but free to start with. So something with a very short wavelength, which sees inside the proton, sees this quark as free. So if we can hit it and see it's free, we should in principle be able to measure its mass. But this is very difficult for light quarks, because this has to be very, very energetic, and it's very hard to distinguish what the mass is if you're hitting it with an energetic probe. So we have to get this by indirect methods for the lighter quarks. And you see for the heavier quarks, the masses come to be rather similar. So you've got these two masses. This is the mass entering into the theory, deep theory. This is the mass that you would if you added up the constituents to make the mass of the proton. Proton is made of 2 up quarks and a down, and you can see that it's coming around about 900 to 1 GeV. Now, experimentalists measure cross-sections for interactions, and they quote them in barns. So, though we're advocating only one unit, GeV, experimentalists are naughty. They give us another unit, barns. One barn, which is 10 to the minus 28 square meters. It's an area. It's an area presented to a projectile, and it gives you a measure of the cross-section. So we should try and convert this barn into our units of GeV. And this is an enormous cross-section by particle physics standards, so even a millibarn is a big cross-section. So let's try and convert a millibarn into our units of GeV. Well, we start with what we had before, that h bar c is the order of 0.2 GeV Fermi, and we square it to get the Fermi squared. So we square that, and we get GeV squared Fermi squared. And Fermi squared, remember Fermi is 10 to the minus 15 of a meter, so Fermi squared is 10 to the minus 30 meter squared. And I want to write it in millibarns, which is a thousandth of this, so that's 10 to the minus 31 meters squared. That would give me a millibarn. And you can see there's just a factor 10 difference. So I've got to multiply this by 10 for this number here. So as this thing is equal to 1, it tells us 1 millibarn is 1 over this thing, which is about 2.5 GeV to the minus 2. So in our units that we're using of GeV, the cross-section is measured, a millibarn is about 2.5 GeV to the minus 2. Remember that this is a length squared, so this is 1 over a mass squared in dimensions. Now the vital thing, if you're making a particle physics accelerator, is how many events you see of the process you're interested in. So people talk about the luminosity of a collider. And a collider is made of counter-rotating beams, red bunches going round this way and green bunches going round this way, and they're conspiring to interact at where the detectors are. And the beams are made in bunches. So we have bunches of particles going round, and the value of a collider is how many particles are interacting with each other. So this is the luminosity, which is the frequency the bunches go round, because if they go round more times per second, they give you more interactions. The number of particles in each of these bunches, so that's K, and then the number of bunches in a ring. And then you've got to divide it by the cross-sectional area that the beams make, how big they are. And that will give you something in units centimeter to the minus 2, seconds to the minus 1. That's what experimentalists quote. When they're looking at an accelerator, you'll see some number 10 to the 30, usually, or more, giving you the luminosity. Now, the number of events of the process that you're interested in with a cross-section sigma in a time t is just multiplying this number by the cross-section to get rid of the centimeter squared, and by the integrated time to get rid of seconds to the minus 1. And that will tell you how many particles you expect in time t. So, for example, at LEP 1, where they were making the Z, LEP 1 had a luminosity 2 times 10 to the 31 in these units. The cross-section of the Z at LEP was 40 nanobarns. So it's not millibarns, it's nanobarns, 10 to the minus 9 of a barn. N means 10 to the minus 9. And so how many events will they get in a day? Well, the luminosity, well, first of all, we've got the cross-section. 40, and we've got this nanobarns. And nanobarns is I've got to change it to centimeters. See, experimentalists are naughty again. They're measuring things in centimeters instead of meters, and now we've got to do the conversion. So 40 nanobarns is 40 times 10 to the minus 33. The luminosity is 2 times 10 to the 31 of LEP 1. And the number of seconds in a day, because we're measuring it in seconds, is 60 times 60 times 24 hours. And if we multiply all this together, we get 70,000 Zs produced in a day. So this is the crucial thing. Given the collider, the luminosity, given the cross-section of the process that you're interested in, you can calculate the number of events. Now let's look at the four forces. And gravity, we're going to dispense with gravity, but just let's look at gravity for a minute. We'll start the four forces, we're starting with gravity. And let's start with Newton's non-relativistic theory of gravity, where the interaction between two masses is just such that the potential is inversely proportional to the distance. The force is proportional to the distance squared. They're attracted with 1 over r squared potential, and then there's Newton's gravitational constant. So that's the potential, the force represented by the derivative of this potential. Now, how strong is this force? How do we work out how strong it is? Well, in our units, let's say these two masses are 1 natural unit of length apart. So what's a natural unit of length? Well, from our quantities that we've got, h bar c and something like the mass of the proton, we can construct something with the dimensions of length. Because this is an angular momentum, a momentum times distance, and on the bottom here this is a momentum, because that's m times a velocity. So these two cancel, and we've got something the dimensions of a length. So that's the natural unit of length. So if these two were protons, this is the natural unit of length between them. So we can measure this gravitational interaction in terms of the rest mass energy of the particle. So here's the gravitational interaction, gm squared for the two protons, the natural unit of length, which is h bar over mc, over the rest mass. This, when we put h bar equal to c equal to 1, just gives us gn mp squared. And if we put in these numbers, we get 10 to the minus 40. So the strength of this interaction is minute in terms of the rest mass of these particles. So you can ignore in a laboratory particle physics experiment. So why is that the force we see? We see it. We stand on the ground here and we see gravity. We don't really appreciate the other forces, though they're of course there, but we do appreciate gravity. And the reason that gravity wins in bulk is that it's always positive between masses. Electromagnetic forces cancel between the charges. You've got as many electrons as protons, so you're neutral, I'm neutral, and we see no interaction. If you had 1% less electrons, and I had 1% less electrons, we'd have an enormous force between us, enough to lift Table Mountain off the Earth. So that shows how strong it is. Because it cancels, because you're neutral and I'm neutral, we don't see the electromagnetic interaction. But gravity is always positive. So that's why we see gravity. But we say we can throw it away. But we have to be careful, because we've said here it couples to mass, but really, in general relativity, it couples to energy. So instead of having gn mp squared, we have gn e squared. So according to general relativity, the coupling will get to the size of 1 when e squared is the order of Newton's constant to the minus a half. And when we work out what that is, that's 1.2 10 to the 19. That's the 10 to the 40, you can see, is disappeared now, because we've got, comes up as the square root now as 10 to the 19 GeV. This is the Planck energy, and at that energy, when the coupling becomes that enormous, gravity can no longer be neglected. But this is an enormous energy, huge energy, way beyond anything we can envisage in laboratory experiments. We would then have to consider a quantum field theory, where just like we're exchanging photons between charged particles, we'd be exchanging a graviton. And as it's got an infinite range, this has to go an infinite distance, so it must be massless. And this coupling of 10 to the minus 40 is a measure of the probability of this exchange. So it's going to be very hard to detect this graviton in present-day experiments. They're trying to push the limits down to visually see gravitons. All we can do is deduce their presence by seeing stars radiating energy away. Now, there's a problem in general relativity. Well, first of all, in general relativity, the quantum field is representing fluctuations of the metric, which has got rank 2, means that the spin of the graviton, if it exists, has got spin 2. Now, on its own, just like this, we've got a problem because it doesn't yield a finite or a renormalizable quantum field theory due to the singularities of this interaction. And a huge amount of current research is concerned with trying to bring gravity, tame gravity, and bring it under control and incorporate it in the theory of the other forces. And I'm sure a lot of the lectures here will be concentrating on that point, because gravity is at the moment outside the fold. We haven't got an acceptable quantum theory of gravity as yet. Let's look at the next force, the electromagnetic force. Here we start with Coulomb's law. The potential now is just the product of the charges and the distance between them. And let's talk about electrons. Well, I'm talking about protons again because I've got a charge plus E here. Actually, it doesn't matter what particle I talk about because the mass will cancel out. So now we have a unit distance, the same unit distance as before, and we have an electrostatic energy of two charges of size E, a unit distance apart, over the rest mass energy. And that dimensionless number is called the fine structure constant, alpha. That's a historical name to call it. It's really just a dimensional measure of the strength of the electromagnetic interaction. So here is the potential. The charges are both E squared over 4 pi epsilon naught. 1 over R is the H bar over MC, and there's the rest mass. Now the mass cancels out in this case, and we've got E squared over 4 pi epsilon naught H bar C. H bar C is equal to 1 in our units, and so we've got E squared over 4 pi, and when we work out what all of that is, it's 1 over 137, independent of what particle we look at, whether it's a proton, electron. It's just the charge that's important. And the smallness of this number is the reason that we can use non-relativistic quantum mechanics for the hydrogen atom, because it means that the effective velocities, if you can talk about velocities in quantum mechanics, are much less than the velocity of light. And particle physicists use heavy-sized Lorentz units for electromagnetic interactions. So that's the same thing as we did for gravity. Now, what about a quantum field theory? In the quantum field theory, again, we're exchanging photons, as we mentioned a bit ago, between charged particles. Again, this force has got infinite range, so the mass of the particle being exchanged is 0. And we'll see later that the photon is described by a rank 1 electromagnetic potential, A mu. It's got a Lorentz index, a single Lorentz index, so it's got spin 1. Graviton was the metric, which had 2 indices, G mu nu, had spin 2. We'll come back to this several times in the lectures. Let's go on to weak interactions. Now, weak interactions began looking at beta decay of nuclei, in which a neutron or a proton inside a nucleus changed to a proton or a neutron. And when this was first looked at, they didn't know anything about a neutrino, so you'd expect the electron or the positron to come out with definite energy, because this would have been a two-body decay without these two. But it had a spread of energies, and Pauli introduced another particle to account for that spread. So this is way back, even in 1930, this was hypothesized as the basis of beta decay. of course, there are a lot more weak interactions. I've just written another one here, the decay of a muon. Now, it has to have very short range because it doesn't affect the spectrum of the hydrogen atom. And so it must cut off very quickly. And originally, very quickly after Pauli hypothesized this, Fermi introduced a point interaction. It's got such a short range, it's got no range at all. He deduced that it had 4 fermions were interacting at a point. And you can see that if these 3 particles are spin a half, this means that has to have an odd half-integral multiple of spin. And so it's also spin a half. And from the rate of beta decay, we can calculate what this coupling GF is, because this is the process that's assumed to mediate this. We know how fast this is. And it comes out that this coupling times the mass of the proton is 10 to the minus 5. So it's weak. It's not as weak as gravity, which is 10 to the minus 40, but it's weak in relation to electromagnetic, which is 1 over 137. Lowest order field theory would be okay, but higher orders gives problems. Lowest order field theory gives you the right answers, but the theory is diseased, so it just appears to be a chance. Now, Fermi's original proposal is essentially correct, except that the interaction is not exactly a point interaction, but is mediated by a very massive particle, which doesn't travel very far. So it's the same picture as this, only if we blow this blob up, we see that there's a particle being mediated here. And this particle, this W boson, this massive boson, essentially couples to the fermion pairs, the quarks and the leptons as pairs universally. It's always G. So it couples to these pairs in the same strength, except for a bit of mixing between the quarks, and nowadays even between the neutrinos. But basically, there's a universal coupling of this thing to all quark pairs and lepton pairs. So let's look at that a little bit more. As we now know that this point interaction is mediated by this picture, we can predict the mass of the W if we assume that this G is the electromagnetic coupling. Let's just see what mass we get. So what we're saying is here is the beta decay process, and it's being exchanged by a massive W going across. And actually, we know that we're going to go from a neutron to a proton, or a proton to a neutron, so we know that there's 2 charges of the W. It doesn't require too much imagination to conceive that there'd be a 3rd charge to the W, 0. And if we've got 3 gauge bosons, it would generate an SU2 gauge theory. We'll discuss this later. And that would give us 3 fields, each of them carrying a Lorentz index have got spin 1, and I being plus, minus, or 0. So that's what we believe the weak interaction to be, with some modifications, which we'll discuss later. But what we're interested in doing is let's say that this interaction is weak, not because the coupling is weak, but because that's a massive particle. And it's harder to throw a massive particle across. That would make it weak. So let's say that this coupling was the same strength as the electromagnetic coupling. Now, G squared here, GF, the real coupling, is the product of these 2 G's times the price you pay for throwing a W across, which is mW squared. This is the price you pay. This is the propagator in field theory language is proportional to mW squared at low energies. So this big coupling, this Fermi coupling, has been taken apart into G squared over m squared, and we're now saying G squared is the same as E squared. So if E squared over 4 pi is 1 over 137, and GF times MP squared measured from beta decay as 10 to the minus 5, we can calculate what the mass of the W boson is, because the mass of the W boson is just E over the root GF. Now the root of GF, square root of this, is 1 over the square root of this, is just 300 times the mass of the proton, times E, which is 4 pi over 137, the square root of. And if we calculate that, we get 100 times the mass of the proton. So this is amazing, because this very rough and ready back of the envelope calculation has given us roughly the right mass for the W. And that would be nice if that was the end of the story, but it isn't. This is not quite correct, because weak interactions are not on their own. They actually mix with electromagnetic interactions, and this mixing weakens, well, actually strengthens the coupling of the weak interactions a little bit due to this sign of the mixing angle here. Sine squared is experimentally 0.23. And so instead of having a nice weak interactions on its own, with a W0 here, the neutral member here mixes with the photon. And we'll discuss this later in more detail. So instead of having a W0 here, we have a Z boson and a photon, which are combinations of the W0 from SU2 and another gauge boson field B. And here's just a mixing. This is a 2 by 2 mixing matrix. These are the gauge eigenstates, and these are the physical mass eigenstates. This doesn't, in the context of these lectures, mean too much at the moment, because I haven't introduced gauge theories, and I haven't introduced this mixing properly. But we'll do that later. That's not the end of the story. The other very curious thing is parity. In other words, you look at somebody, they look symmetric left and right. You would think the world was symmetric under interchange of left and right. In weak interactions is maximally violated. Couldn't be violated more strongly. It's because W bosons couple only to left-handed quarks and lepton states. They don't couple to the right-handed, so it's totally one-sided. For relativistic particles with energy much greater than the mass, a left-handed state is the same as the spin projection of the particle being against its momentum. So that would be a spin projection, if it was a spin a half, minus a half in that direction. A right-handed would be plus a half in the direction of momentum. And this is called the helicity. This is helicity plus a half, helicity minus a half. So left-handed is the same as the spin projection against the direction of motion. And that could be, once this was asserted, it could have been checked at any time, but the assertion had to be made, and within 6 months they found that this indeed was true, that parity is maximally violated. There's another big puzzle in particle physics. Why is parity maximally violated? Now, massive gauge bosons give rise, for a gauge theory, they should be massless. So the field theory turns out to not be renormalizable. And the problem is due to the longitudinal polarization states of these particles. Again, that's something we'll come to. So it looks as if this theory is going nowhere, but then it's saved by the Higgs mechanism. And what happens is we introduce, and we'll discuss this later, we introduce another particle which has spin 0 in the terms of the doublet, like the up and the down, but now it's a spin 0 particle. And these 4 states, because this is a complex doublet, 3 of them get eaten. We say they get eaten by those to give the third spin state of each of these particles, leaving one field left over, which is the Higgs particle that we're all desperately trying to find. That would be in the standard model. So we've got one Higgs, and the other 3 fields are eaten to make these particles have mass. So that's a very brief pen sketch of weak interactions. let's go on to strong interactions. Now, in the 1960s, the strong interactions were thought to be mediated by pion exchange, or the lightest particle, the lightest hadron, the lightest strongly interacting particle. A hadron is a strongly interacting particle, was the pion, and so that could be thrown furthest across. And so, in analogy with electromagnetic interactions, let us try a field theory based on this. It will not work because when we work out the strength of this nucleon-nucleon interaction from its cross-section, we find that the coupling over 4 pi in this case is the order of 15. And that's much too big to use perturbation theory, which is the basis of quantum field theory. So field theory is out, it appears, for the strong interaction. In 1960s, it looked in the 1960s as field theory was just an accident for the electromagnetic. We didn't know enough about weak interactions. That we knew that the lowest order seemed to work, but we didn't have a field theory. Here we don't have a field theory. So field theory was not at all in vogue. And people believed that this interaction could be explained by imposing analyticity, crossing, and unitarity. This is being called high-class kinematics, really, on the probability amplitudes for a process. We'll discuss that very briefly in a minute. The idea, if you impose that, is there'd be only one solution that nature would adopt, and that would be the solution of the world. In other words, the particles would bootstrap themselves. This approach failed. And so in the 1960s, there was a terrible dilemma as to what to do with the strong interactions. Now, from the mid-1960s, first, we had a lot of particles by then had been discovered. I've only put a few here. And these are strongly interacting particles. So a lot of strongly interacting particles, besides the neutron, the proton, the sigma, the lambda, the pion, kaon, rho, etc. And they form multiplets of particles of similar properties. And they suggested that baryons, from looking at these multiplets, were made, baryons are the half-integral spin, and mesons are the integral spin. Baryons appeared to be made of 3 quarks, and mesons a quark-antiquark pair, where these, as we've seen, have spin a half. So we're going back to the mid-60s to see the beginning of the quarks emerging from physics. So quarks were the building blocks of hadrons, but it was necessary for statistics to make, because this state looks symmetric, we want it to be antisymmetric under interchange of 2, to give them a new quantum number, color. Now, deep inelastic scattering confirmed the existence of quarks by trying to... It looked as if they were free, and this interaction did look as if they were free, but we never saw them escape. So there's a kind of dilemma there. It transferred the confinement of quarks, which are never seen, to the fact that color is confined. And from this, we're able to deduce, well, using color now as a basis of a gauge theory, we found that we could explain this dilemma. And it turns out that these gauge fields, in this case, were colored. Now, I thought I would start at this, discussing the strong interaction, discussing this, because this really is a great adventure story. This slide here is a great adventure story of particle physics. And to see, going from the mid-60s right down to gauge theory. So let us do this gauge theory first. So we're going to now, we've done the overview of the interactions. Probably we haven't understood anything deeply, but now we're going to look at it in more depth. And let's start with this one and go through the history of this before we go on to things like the Higgs mechanism. So let's go back to the beginning, because this is a really lovely adventure story. So we're going to start with strong interactions, and we're going to start right from the beginning. We're going to take a nucleus, And in a nucleus, we've got protons and neutrons. And the protons, as we've said, have got an electrostatic repulsion between them that's enormous. We mentioned that it was enormous. But they are not ejected from the nucleus, so there must be some other force, short range again, which is more attractive than the repulsion from the electrostatic. You know that if you put in about 100 or so of these, then the nucleus is not stable because you're putting so many in together. But you have to put a lot in together to get over this strong attractive force. Well, we're only looking at the strong force, not the weak force. Now, isospin, from looking at the nuclear data, it appeared that if you ignored the electromagnetic interaction, nuclear physics was symmetric under interchanging neutrons and protons. In fact, you could even have a group theory. You could do rotations in this abstract neutron-proton space. And so you had a group theory very similar to the group theory for angular momentum. So this is the angular momentum where you've got a spin up and a spin down for those are the two values of Jz. In this case, you've got an abstract space with isospin up and isospin down. This was a doublet. And isospin was verified in nuclear physics. Well, all these particles started to pour out of experiments in the 50s and 60s. We started to get hundreds of them. And I've written some here, baryons which have spin a half or 3 halves, and mesons with a spin 0, 1, 2, etc. To begin with, they were seen by putting emulsion stacks into an aeroplane or taking emulsion stacks up the top of the Pyrenees mountain. And there's this lovely quote by Powell. It was as if, once he looked at the emulsion stacks, it was as if suddenly an entry had been gained into a walled orchard where protected trees had flourished and all kinds of exotic fruits had ripened undisturbed in great profusion. So suddenly, although they were there, they hadn't been seen, and then suddenly all of these particles were found. And we can group these particles together. Well, first, let us dispense with this bootstrap idea. Let's go back to the bootstrap. The bootstrap idea, remember that what is the theory of the strong interactions? We mentioned that the electromagnetic exchanges, the photon, and we said, well, why can't we exchange all of these other particles and try and make a theory from exchanging these particles? So let's just present a picture as to what they were trying to self up by your own bootstraps. So the idea was, given those particles, they all just generated themselves. And here's roughly what was going on. This is this high-class kinematics, crossing analyticity and unitarity. So, and it's done very sketchily here. Let's take a process with the lightest particle. Let's take this process, pi minus to pi minus pi minus. And that's physical in this region of this plane. Don't let me define it too precisely. So it becomes physical in this dotted region. Now let me use crossing, in which I interchange this particle with this one. So if I take this over the other side, it becomes a pi plus, and this becomes a pi plus. So I've got pi minus pi plus to pi minus pi plus. So crossing the blue particles is taking me to another region of this kinematic plane. Now, in this region, I can interchange a rho meson. That's the lightest thing I can do. It's neutral here, and I've got a neutral rho meson. Here, I would have a charge 2 particle, and there isn't one. So at a certain energy, and this measures the energy, I get the rho meson, right sticking on that mass as a resonance there. So this is kind of a resonance. Now, if I interchange these two, I get another kinematic region here. And it's the same process. So I've got a rho meson in this region. Now you've got to imagine this sheet. This is representing the amplitude with a pole here and a pole here. And then analyticity links these three regions together. And the nature is such that from these three things, you can bootstrap the row in this way. So the row is picked out by just looking at this process here and studying what you get here, you would hopefully just get the row out. So could the row just come from measuring this? And this failed. It failed because you can just add an arbitrary pole and it doesn't change anything. You still can satisfy analyticity, unitarity, and crossing. Now, the other thing we need is statistics. And so we need a bit of quantum mechanics. We know a particle behaves as a wave. And if we look at electrons in an atom, for example, in some state in an atom, we'll have a wave function like this, a radial wave function. Maybe this is the 1s, and maybe we have a 2s. The Pauli exclusion principle says no two electrons can be in the same state, and it comes from the antisymmetry of fermion to fermions. And so particle A could be in state 1, particle B could be in state 2, or vice versa, we can't tell. And because it's a fermion, we've got a minus sign. And so if A is equal to B, this vanishes. And so we can't have two in the same state. And from this, we get the periodic table. You just build up the electrons. The electrons have to continually go into higher states. And it's coming from this minus sign for fermions. Now, and this is because electrons or fermions are antisymmetric. Photons with spin 1 have got a plus sign. They love each other. They like to congregate together. These repel each other. They hate each other because of the minus sign. Photons love each other for the plus sign. And, of course, we get lasers. We just get more and more photons together. Now, electromagnetic force have, because here's an example of a calculation in which we're calculating the anomalous magnetic moment of the electron. Well, first of all, let me say the basic interaction in QED, and again we'll come back to this, is the photon coupling to a charged particle. And then you just bolt this together in all possible ways. And every time you bolt it together, you have a coupling E at the vertex. So that's got E squared. This is E to the fourth. There's another E to the fourth. And I'm just bolting together this diagram in different ways, making up higher and higher diagrams in this perturbation series. And as this number is small, these terms get smaller and smaller. Apart from the fact that we've got loops and we've got to renormalize the theory, let's forget that at the moment, but you can see that perturbation theory should hold, and if we can renormalize it correctly, which we can do very precise calculations. And here, some of the most delicate experimental measurements. This is the departure of the magnetic moment from its Dirac value of 2, and these are the most intensive computer calculations conceivable, and you can see the agreement is remarkable, way down in many, many parts per billion. And we've mentioned that we cannot repeat this field theory for strong nuclear interactions. Perhaps I should stop at this point. I've been going. Should I have another 5 minutes or not quite an hour? Okay? Or do you want to ask questions? I'll just go for another 3 minutes. So, we've said that all of these particles are being found experimentally, and we're dividing them into mesons and barons. These are strongly interacting particles. The first thing that was seen, they were produced, these new particles were from, these are the particles that we started with, pions and neutrons and protons. These other particles, some of these other particles were only produced in pairs, and this indicated that there was a new quantum number. A new quantum number would explain why they're produced in pairs, and you give one of the particles a strangeness, an additive quantum number, 1, and the other particle a strangeness -1. So this process here, this has got strangeness 1, this has got strangeness -1, these are non-strange, so it goes. But this one couldn't go because both of these particles have got strangeness -1. So some reactions happened and some didn't, and that introduced this concept of strangeness. So, having strangeness, we can plot pictures of particles of similar properties. Let's take all the baryons, which are roughly the same mass, and let's plot strangeness on one axis, and let's plot them with a charge like that to make them as symmetrical as possible. To cut a long story short, we're putting the neutral ones there, negative ones, positive ones. If we look at the baryons with spin 3 halves, and then we put strangeness up in this direction, the neutral ones here, charge minus, charge 0, charge plus, and double. So this 3 up quarks would make the one up. 3 down quarks would make this one, be half integer spin. The quark, and here's the multiplet of the antiquark. And if we combine either U or D, strange quark, a little bit heavier, this was 1 light quark. These are spin 1/2, and so from 3 up quarks, because